Introduction to Optimization, question for screen recording task, part 3, Unconstrained Optimization. Question 9, Derive Rank-One Quasi-Newton update. The Newton method. The Newton equation is Fk plus Jk dk equals 0, where Fk is our equation system, Jk is the Jacobian of F, and dk is a multidimensional vector. The update of xk plus 1 is xk plus alpha dk, where alpha is a scalar of our choice. So we know that the solution for this Newton equation is d equals minus hk inverse multiplied by gk, where gk is the gradient of fk. D helps us to find the minimum solution of the Newton equation. The computation of the Hessian and its inverse can be very heavy. So we want to find an alternative method that won't require us to compute the Hessian for every step. So, annotation. We will annotate pk to be xk plus 1 minus xk, and we will annotate qk to be the gradient of f in xk plus 1 minus the gradient of f in xk. The quasi-Newton method. We will use an approximation to the Hessian and its inverse. So, we know by definition that the differential of the gradient of fx is the Hessian multiplied by the differential of dx. So, we can write, substituting and using our annotations, that hk plus 1 multiplied by pk equals to qk, because dx is xk plus 1 minus xk, so it also can be written as p, and the differential of the gradient fx is the gradient of fxk plus 1 minus the gradient of fxk, and it can also be written as q. So we will use a rank-one update for the Hessian. We have the Hessian of hk plus 1 equals the Hessian of hk plus a rank-one matrix. The rank-one matrix can be written as a multiplication of a column vector u with a row vector v transpose. And we have to find u and v. So computing u, we have the secant equation and we have the rank-one equation. So we will take the rank-one equation and substitute hk plus 1 into the secant equation. By doing that, we get that hk plus uv transpose multiplied by pk equals qk. We will open the parentheses and get hk pk plus uv transpose pk equals qk. We will move hk pk to the other side and get uv transpose pk equals qk minus hk pk. And now, because we have here v transpose pk, we know that it's an inner product by definition and it's a scalar. So we will divide our equation by this expression and get that u equals 1 divided by v transpose pk multiplied by qk minus hk pk. Now, using the u we found and the rank-one update equation of the Hessian, we get that hk plus 1 equals hk plus 1 divided by v transpose pk multiplied by qk minus hk pk v transpose. We know that the Hessian has to be a symmetric matrix, and we have a sum. So we know that each matrix in the sum can, if each matrix in the sum is symmetric, so the Hessian is also symmetric. So we know that the Hessian hk is symmetric by definition, and we only have to make sure that this element is symmetric. We will choose v to be equals to qk minus hk pk, and then we will get the expression hk plus 1 equals hk plus 1 divided by v transpose pk multiplied by v transpose. We know that this is a scalar. This is a symmetric matrix, because if we transpose it, we get the same matrix. And so we get that a sum of symmetric matrices is also symmetric, and our Hessian hk plus 1 is symmetric. Now we will try to find the inverse. So we will annotate bk equals the inverse of hk. So using this annotation and the secant equation, we know that bk equals the inverse of the Hessian. So we also know that the Hessian equals the inverse of bk. So we write it in the secant equation and get that bk plus 1 inverse multiplied by pk equals qk. We will multiply it by bk from the left and get that pk equals bk plus 1 qk. Now we will look for a rank 1 update for the Hessian inverse. We will write the rank 1 update as an equation to be bk plus 1 equals bk plus uv transpose. And now we have to find uv that makes the rank 1 update we want. So we have the secant equation and we have the rank 1 update of b. So we take the rank 1 update and put it into the secant equation. So we get pk equals bk plus uv transpose qk. We will open the parentheses and get pk equals bk qk plus uv transpose multiplied by qk. Now we will move our elements uv transpose qk to the left and pk to the right, and we get uv transpose qk equals pk minus bk qk. And now, since we know that v transpose qk is an inner product, it creates a scalar, so we will divide by the scalar and get that u equals 1 divided by v transpose qk multiplied by pk minus bk qk. Using the u we found and the rank 1 update for bk, we get that bk plus 1 equals bk plus 1 divided by v transpose qk multiplied by pk minus bk qk v transpose. As before, we want to maintain bk plus 1 symmetrics because an inverse of a symmetric matrix is also symmetric. So bk is an inverse of the Hessian, so it's symmetrics, and we want this element to be symmetric. So as before, we will choose v to be this expression, and we get v equals pk minus bk qk, and then putting it into the rank 1 update equation of b, we get that bk plus 1 equals bk plus 1 divided by v transpose qk, vv transpose. And this is symmetrics. This is a scalar. This is also a symmetric matrix. And then we get that bk plus 1 is symmetric. So to conclude, the rank 1 quasi-Newton update of the Hessian is a k plus 1 equals hk plus 1 divided by v transpose pk, vv transpose, where v is equal to qk minus hk pk. And the rank 1 quasi-Newton update for the Hessian inverse is bk plus 1 equals bk plus 1 divided by v transpose qk, vv transpose, where v equals pk minus bk qk.